Welcome viewers. In this video we'll see the synchronous motor on load in that variable load and constant excitation. Subscribe the channel for more videos and notifications. Soft copy of this material available in the drive. The link is given in the description box. Now we'll go to the topic. So in the previous video we discussed synchronous motor on load in general case. When it is loaded, what happened? When it is not loaded, what happened? During the no load condition, the EB is equal to V phase. Both are equal in opposite direction. In case of it is loaded, the fluxes are stretched on one side, so it will form the torque angle delta. So based on that, this EB and P's are not equal. There is some phase displacement happen in the EB with an angle of delta. So you can refer that video for synchronous motor on load. It's a continuation of this. From that topic is a continuation. Operation of synchronous motor at variable load and constant excitation. So from that previous we are able to understand, as the load on motor increases, the load angle delta also increases. So that detail available in previous video, how it is increases. As delta increases, though magnitude of EB and V are constant, the displacement from EB from the initial position increases. So when the load increases, load angle delta increases. When the delta increases, the phase displacement, the displacement of EB is increases. Even EB and V is constant. So load increases, delta increases, phase displacement of EB increases. So the resultant vector ER equal to V phase minus EB, that is equal to IA ZS. That is a general case we discussed in the previous video also. So there's difference. Therefore the vector difference between V phase and EB increases. Therefore ER increases, which means that IA ZS increases. Since ZS is constant, IA increases as a result of increase in ER. So finally we got that IA also increases. So the load angle increases. When the load increases, delta will increase and phase displacement E will increase. Because of increase in ER, IA ZS increase, but ZS is constant, so IA increases. Right? Load increases, load angle delta increases, phase displacement E increases, finally the current IA increases. That is the result we got. Now let us see the vector representation at light load and heavy load. Okay, so that the topic is variable load and constant excitation. In that variable load we have two cases, light load and heavy load. Now we'll see the light load. So this is a phasor diagram. This V phase available and EB. V phase and EB are in the same line. In case of no load condition, both are in the same line. Because of loaded, it is displaced by an angle of delta. In case of no load, EB and V both are in same line. But here it is loaded, in that it is light load. So it is displaced with an angle of delta, this EB. The vector sum of vector difference between EB and V phase is E resultant. This ER is the difference between vector difference between EB and V phase. So this angle here also delta. Now we discussed that IA also increases, so IA available opposite to that EB. So that angle is theta. That is the angle between IA and ER. The angle between V phase and IA is pi. Right. Now we'll see what happened. So V equal to EB. When load is light, delta is small. Here VB is not equal, but in case of light load, it may be equal. EB displaced by delta. Resultant voltage ER equal to V phase minus EB. Resultant current is at IA at an angle of theta from ER. The angle between V and IA is pi. So in the light load, this IA, this angle delta is small. In case of heavy load, next we will see that it will be more, but here it is small, right? So there is a phase displacement between EB and V phase by delta, and resultant current IA, that's angle between ER and IA is theta, V phase and IA is pi. So finally what we concluded, that delta is small in case of light load. We'll see what happened in the heavy load. So this is the heavy load. So almost the phasor diagram almost same, only the thing is the heavy load angle delta is large, this angle is more. So V phase, EB is displaced by an angle of delta. The vector difference between EB and V phase is resultant voltage ER. The current IA is exist, that is opposite to the phase of EB. The angle between IA and ER is theta. IA and V phase is pi. That's what we discussed earlier is same, but only thing, the angle, this angle is more. EB is again displaced by an angle of delta. Now EB ER resultant voltage equal to V phase minus EB. ER now moves towards voltage ER increases. So the current IA also increases, and angle between voltage V and IA also increases. What is that V and IA? This V and IA. This pi also increases. So for light load, the torque angle delta is small. For heavy load, the torque angle delta is more. That is the difference. Now we'll see the constant excitation circle. So this diagram refers the constant excitation circle. What we discussed same thing, but we have different values of delta. So this is V phase available. This EB1, the back EMF EB1 with an angle of delta 1. EB2 with an angle of delta 2. EB3 with an angle of delta 3. So the vector sum of difference of EB1 and V phase is ER1. This line is clearly given. The vector difference of EB2 and V phase is ER2. The vector difference of EB3 and V phase is nothing but ER3. So we can go like that. So by locus of this ER1, ER2 will give the constant circle, constant excitation circle. That means when the delta increases, there is a resultant voltage ER also increases. This V phase is remain constant. This keep on increases. On other side, the current also changes. IA1, IA2, IA3. Similarly, the angle is theta 1, theta 2, theta 3. Here pi 1, pi 2, pi 3. What we discussed earlier, same thing. Only thing is this locus. Based on the locus, we can draw the constant excitation circle. Right? So V phase available. Here EB1, EB2, EB3 displays with an angle of delta 1, delta 2, delta 3. So these are all the vector difference, ER1, ER2 and ER3. Now we'll see the detail. For constant excitation, when the load is varied, then delta keep on changing, due to which, so when the load increases, what happens? The delta increases. So ER equal to V phase minus EB, that is equal to IAZS, keep on changing. So the locus of this ER, that is IAZS, is a circle. So we see the part of the circle. So delta increases, IA increases, and then delta decreases, IA decreases. So with that we can conclude that delta and IA is proportionate. Delta increases mean IA also increases. Delta decreases mean IA also decreases. Right? So the synchronous motor on load, general case, previous video available. This video, variable load and constant excitation circle. Here we are discussing IA. In previous video, the IA is not available. Only V phase and EB. Then resultant voltage ER. Here we are discussing with IA. What happened to the IA? What we concluded? The delta, when the load increases, delta increases, EB increases, thereby IA also increases. This locus of ER will give the circle. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. The link is given in the description box. Thank you for listening. All the best for your examination.